So there is a we're trying to find more sophisticated ways of evaluating convergence of series, evaluating convergence. So as you can see, not evaluating the sums, but rather just finding out whether a series is convergent or not. So this is the ratio test is right there. You can just look, if you look carefully. There is no word spoken about what the sum is, only that there is a sum. So convergence means that there is a sum, and then extra effort might have to be taken or needed to figure out what it is. So at this point, we only care about convergence, and you'll see shortly how that works out. So the ratio test is derived from the idea from what we know, what we initially developed for a geometric series. And then this is the result. The geometric, if the series is geometric to begin with, then the ratio test does not produce any new information. But if it does not, if it is not a geometric series, then this is a very nice way to find out what's going on. So you take the ratio of the elements divided by the previous element, okay, and then that is supposed to be getting smaller and smaller and smaller, and but in what sense? In the sense of its limit. Okay, so that's what that limit is. So that R is like it's an analog of the ratio of a geometric series, and if that number is less than 1, we have convergence. If it's larger than 1, we have divergence. Okay, so that's really the whole story. Compute the limit, and then you know the answer right away, unless the test fails. In more extreme cases, which we have seen. That sometimes the test fails, and those especially at when we move on to series, specifically to power series. Okay, so that is what this example is about. So rather than looking at the series at one point, every element of the series is a number. We have now all the terms depend on x. Okay, so then convergence also depends on x, and therefore the ratio test is applied. Even though simultaneously at the same time to all values of x, at the same time it is give the different answers for different x's. So these are the different answers that you can see here. So the absolute value of x is less than 1, that interval, then the answer is yes, because that R, the substitute for the ratio, is less than 1. And if it's outside, then the outside of that interval -1, 1, you have the ratio larger than 1, and you have divergence. Okay, when it is equal to 1, that is a separate question. Not as important as the rest. You can compare just exactly 2 points versus the infinitely many. But we did it anyway, and as you can see, we have discovered about this particular the simplest, I suppose, power series. So as you can see, that this is my power series, and it has nothing but x's with no coefficients whatsoever. And turns out that it converges on the interval, open interval -1, 1. So that's what we have at the bottom, and elsewhere it diverges. Okay, so the idea that also came up and becomes more important is what the importance of the sum of this series. And as we have discovered, not discovered, but rather we went the opposite direction. We started from a function, and then we discovered its series. Okay, so and we discovered its series. So that's what is that function, and that function is in fact 1x. Sorry, 1x plus 1. 1x plus 1. That's the original function, and that is, as we're gonna discuss shortly, is the sum of the series as long as we stick with x's between -1 and 1. Okay, but at this time we were just still talking about series, numerical series, not power series. This was just an example, even though quite an important one. Okay, so this was this one is the transition from the ratio test to power series, or rather application of ratio test to power series, not just one power series as in that example, but all of them simultaneously. And then turns out that that ratio, that the limit of which we have to compute, simplifies very nicely into that expression over there, and we end up with a corollary which provides us with convergence information about the power series. In general, as long as that limit exists, obviously that's to be kept in mind. As long as that limit over there exists over here, then we have the answer. Then what we have is, at the very least, we have an integral of convergence that is centered on that point A, the center of the power series, and then divergence outside of that interval. Okay, so the endpoints are not covered by the theorem, just as much as the possibility of the limit not existing. Okay, so limit equal to 1, no answer, or limit does not exist, once again no answer. Okay, but this is pretty good. So that's a starting point. We don't stop here, and it turns out there's another way to look at the geometric series. So geometric series, once again, which is a plus ar plus ar squared ar n. Okay, so r is the ratio, and then what we have used the fact that, so this is a naught, a1, a2, an, and an plus 1 is this. Okay, so these are the terms of my series, and they just happen to have this special form. Okay, and then what's so special about what's so special about the ratio? It is very simple. An plus 1 over an is equal to r. That's where the ratio comes from, in the word ratio, and then we look at r and we say, well, r is less than 1. Convergence. R is larger than 1, divergence. Very simple. That's the geometric series test. Okay, but that is, we just chose we went this way from our geometric series. Every time we multiply by r, we realize what r is. It can be computed in a recursive way, so through as a ratio. But there is another way. So that's number one, and this we ended up with. Well, number one, and then what we did we proceeded on with a ratio test. With in general, we just take an plus 1 over an and look at. By the way, this maybe we'll do it this way. I'll kill the absolute value here, and I put the absolute value with the ratio. So the ratio of absolute values is what we're looking at. So that's our ratio of the geometric series. If we now compare a general series, not this specific series, then that ratio is not a number, but it varies, and then we look at its limit, and then we put some number r there, and then this property is still satisfied. That's the ratio test. Okay, so comparing general series to ratio to geometric series in one specific way. There is another one, and so there's another way to acquire the ratio from the geometric series, and that's taking the nth root. Okay, so instead of going in the consecutive elements and comparing them, we can just take this element over here and take the nth root. So what I'm going to do is I just take what is it, an. I take a and divide by a my initial element, and then take nth root. Okay, so there is no comparing consecutive elements, since we have an explicit formula. Just as well, we have our ratio. Okay, so once again, this is what happens in the geometric series, and then but the conclusion is still the same. It's the same ratio. So we once again have r less than 1. We have convergence. R larger than 1, we have divergence. It's the same. It's the same r and the same geometric series. But if we go on to general series, then what we have is called the root test, which works in exactly the same fashion, except we form a ratio. We form a ratio of we form a root. Instead of ratio, we form a root. Okay, what root of the nth element of the sequence? Well, let's just go with this nth root of well, I need an absolute value here. I need absolute value here as well as here. Okay, so we don't have, turns out we don't have to worry about A because convergence of the, why don't we care about A? Because convergence of the series is independent of the coefficient. Remember, convergence multiplied by any number, as long as it's not equal to 0, will give you another convergence series, and vice versa. Okay, so we're looking at then at this number and this limit, and once again it has to converge to some number r, and then we'll just we have the same, it's the same r. So once again we are relying on this classification. So a certain number appears from a limit, and that number is then used to classify, to discover the series, discover what it does, converges or diverges, and that's what we have here. It is repeated. It is easy for the geometric series, but then now for non-geometric series, you can do it in two ways. Either take the limit of ratios, that's the ratio test we talked about, and now the new test to be stated is the root test. When you take the nth root of, well, what's the nth root, by the way? What's the nth root? How do you define the nth root of x? It is a number y that satisfies a certain property. What is it? Well, if you know what the square root is, then you should be able to think of the meaning of the nth root too. Well, yeah. You know, I would rather go. I would first understand the root, and then I would take that interpretation, that what you have in mind, which is fine. But that is the secondary interpretation. It's more. It's very helpful, obviously, to think about roots as powers, and we have, and we will. But that's not where it comes from. If you want to compute the nth root of x. You need to know what it is, where it comes from. It does not come from the power. It goes the other way around. So from understanding roots, you will understand powers. Okay. So how do you understand roots? You understand them in a very simple way. Y to the nth power is equal to x. Okay. So it is the inverse. Nth root is the inverse of nth power. Once you understand that, then you can deal with rational powers. So then. You interpret rational powers such as 1 over n as nth roots. Okay, so but how do you know what nth root is? That's how you reverse nth power, or inverse rather. So the inverse, two functions, remember, inverses of each other. Nth root, nth power, they're inverses of each other. It's just the same way as sine and arcsine. What is it? Logarithm and exponential function and logarithm, they are inverses of each other, and if you understand one, you can understand the other in just by reversing things. So if we understand nth power, which is at the bottom, then we understand nth root, and from that we understand 1 over n power. Okay, and then if you go on, you can proceed from this on. So this is the order of things. How we understand x, m, n. How? Well, this is simply x 1 over n m, right? So that way you can understand all rational powers as simply the combination of a power, integer power, and a reciprocal power. Okay, so combination, two consecutive computation. You take mth root, and then you nth root, and then you take mth power. That's your rational power. So that's how to understand powers. So as you can see, so we have used nth power. In the geometric series, if you want to represent it explicitly. Over here, if you prefer, this is recursive recursive definition of the geometric series helps with the ratio test. Why? Because an plus 1 is equal to an multiplied by r. That is recursive. On the other hand, there is a direct formula for geometric series. It's simply an is equal to a times r to the nth power. Okay, so depending on which of the two you prefer, or which one of the two you pick, you will end up with a different test, or for r, the different formula for r, as well as different than if you step away from the geometric series. Then there are two different tests on convergence based on these two separate ideas. So once again, either you need an explicit formula, or you are just doing a recursive idea. Even though typically if we study a series, it's probably given by every element of the sequence is given by explicit formula. So that's why, well, but the two formulas are equally applicable almost virtually every time you try it. The only time the root test does not apply well, it is when you have factorials, which is exactly the example that we saw. What happens if my sequence has factorials in it? What happens to the ratio? Very nice. It works out very nicely here. Here's where it happened. If the formula has factorials in it, they cancel out when you divide. Your n factorial, all multiples up to n in the numerator, all multiples to n plus 1 in the denominator. If you divide, you're left with n plus 1. That works out very well. If you try to apply this the ratio test to this sequence, the root test to this sequence, you'll take the nth root, and that's not gonna work out as easily, even though 2 to the n works out fine. But what is the meaning of nth root of n factorial? Okay. Well, certainly it can be worked out. It's just that we haven't discussed that. So in that respect, the ratio test works out better usually. But the results should be the same. If as soon as I state the theorem itself, that should become clear, because we're speaking of the same. We're speaking of the same sequence. So we can apply the same test, or rather the two tests to the same sequence. So then the results should be the same. So let me state the root test. Okay, so we have a sequence or a series. Sum an, once again, it is an abstract series with no restriction whatsoever on it. And we suppose that our limit, very similar to the one in the ratio test, exists. Nth root of the absolute value of the nth element of the series. Okay, so so it exists as a number, possibly 0, or even infinity. So infinity, it is possible. Also possible. It even though it's not a number, it provides us with helpful information. Okay, then we have two cases similar to the ratio test. It's the same R after all. So if number 1, if R is less than 1, this series converges absolutely. Otherwise, it diverges. So then R does not exist, or R equal to 1, but this is 1 here, sorry about that. The test fails. Okay. It could be 0. 0 is fine. 0 is fine. Okay, so as an example, once again, if I pick example similar to what we just saw, how about I take 1 over 3 to the n? Okay, this one is easy. Well, I'm sorry, that's a geometric series, so I don't want to do it. How about n over 3 over n? Okay, so from 0 to infinity. Okay, so this is my series. It's not geometric to begin with. We don't want to apply these tests to geometric series because it's just a waste. Another geometric series. It has okay, so well that's all there is. And then we just look at the nth element, which is n over 3 to the n. We take its nth root. We take absolute value and then nth root, so nth root of n 3 to the n, and then we distribute. So we have the nth root of n divided by nth root of 3 to the n. Naturally, the denominator simplifies. What's the denominator simplifies into? So read it consecutively. So one a term is inside of this operation. So nth, the order of operation is take 3, then take it to the nth power, then take nth root of it. Okay. So 2 consecutive operations with 2 of the operations related to each other. Nth power followed by nth root. What's the result of such an operation? Yeah, so right, so it doesn't do anything because those 2 operations cancel out. That's what inverse means. Okay, and then in the numerator we have nth root of n, and I'm not sure what at some point I do believe that it is may have, I don't think we actually discussed it, but the limit of the numerator is 0. I'm sorry, the limit of the numerator is 1. Okay, so nth root of n, so it cannot be less than 1, but it is 1. So the limit is 1/3. So there are certainly different ways to do it, but let's just take for granted that the limit of the numerator is 1, so the limit of the whole thing is 1/3, and so division then by the inequality. This is my r, and that is my r, that to be compared with 1, and then I conclude that since it's less than 1, the series converges. Okay. So some might be more complicated than that. I don't want to overemphasize them, but you can imagine what happens is, so once again, if you have a factorial, then without establishing a good relation between the roots and factorials might be harder than just go with the ratio test. You can see this worked out fine. Let's just confirm. So this is by the root test. But it will work out, will produce the exact same result if I apply the ratio test. How? I just take an plus 1 divided by an. So in other words, I have, for the numerator, I have n plus 1 divided by 3 to the n plus 1 divided by 3 to the n plus 1. That is n plus first element. Nth element is, formula is right there, so it's n divided by 3 to the n. Okay? Things cancel out, so I have, let me just distribute it first. So n plus 1 divided by n, okay? Multiplied by 3n divided by 3n plus 1, okay? I have, the first term remains, n plus 1 over n. And the second one is I canceled out, and I'm left with 1/3. Okay, so what remains is just to know what the limit of n plus 1 over n is. What is it? N plus 1 over n, where does it go?
It goes to 1.
It goes to 1. How do you know, just in case? plus 1 over n. Well, if nothing comes to mind, go back to calculus 1, x plus 1 over x. Then maybe you might remember something from calculus 1 that helps. Another way is to, this one can be simplified, not that it always helps. 1 over plus 1 over n. Okay, so two terms, one is 1 over n. Where does 1 over n go? It goes to 0. So the whole thing, what remains then, what's in parentheses goes to 1, so the whole thing goes to 1/3, right? So it could be as simple as that, or sometimes you might need a L'Hopital's rule or some of the other rules for finding horizontal asymptotes if there is a limit to be found. You can certainly imagine that doesn't work out. But since we had applied two seemingly very different tests to our series, and they produce the same exact result. In fact, not only they're both produce the same result, so series converges, but also in fact that R that we have discovered is in fact the same. In either case, it's 1/3. Okay, so in a similar fashion to the ratio test, our next concern would be a power series. Okay, so with the several possible outcomes. So power series centered at a point. Point A is here. Okay, and then we applied over here. We applied the ratio test to this power series. And that's how we produce the outcome that the series has to converge on an open interval and diverge outside of that interval. With what's that red is, it is 1 over. It is a reciprocal of our limit. Okay, so similar idea comes up, exactly the same. So the result is virtually identical except to the ratio test. So this one is comes from the ratio test, but what if I have it from the root test and the result is virtually the same? The only thing that changes is this. So replace this limit with the limit that we just discussed. So Cn, nth root of Cn. No, it doesn't fit there. So if it is a root, then we are talking about limit nth root of Cn absolute value, and it is once again equal to some number r, and then the conclusion still works out in exactly the same way. It is the same number, and naturally if you apply to different tests asking the same question, but you apply to the same series, then they're supposed to produce the same answer. Otherwise, what's the point? So indeed, if a series, according to the ratio test, it converges on this interval and diverges outside, there is no other the way the root test would produce a different result. It produces the same. Okay, so that is why that number r in the root test or ratio test is the same number. Okay, so but the possibilities are what we're turning to right now is the patterns of convergence of power series, so that we can make our way back to functions, because that's our goal ultimately. Not really study one series at a time, but rather look at how functions are approximated. Except we're approaching it from a different direction. So not from functions to series as what we have started with, those are Taylor series. We're going backwards. So suppose we have a series and it converges. It produces a function. What can we say? Well, how and under what circumstances, what kind of function it is, what kind of algebra we can do with those functions, and stuff like that. So that's the pretty much the last topic of the course is power series and functions that they produce. Okay, so power series. They produce. Okay, so as an example, so yeah, I don't have to go to general just yet. Power series sum 1 over n factorial xn. That's a power series, and then this is the transition. It turns out to be the exponential function. So power series is starting point, and then if we're lucky, we find its sum, and we'll find a matching function for it. That's what, well, that's not how it happened, but it could have happened this way. We went the other way, right? From the exponential function, we went to the series. It would be pretty hard to guess otherwise. And then it works out for all x in between negative 1, between negative infinity and infinity. Okay? The second example that we just saw is xn. And once again, we discovered that it is 1 over x plus 1. Once again through Taylor series, except this is not true for all x, but for all x in negative 1, 1. Okay, so once again, going from this time we're going from right to left. Let me bring up those illustrations again that we, this is one illustration. As you can see, the picture goes the original way. From the function in green, that function in green is this, plotted right here. So from this function in green, we found its approximations with Taylor polynomials. That's the original idea was. Now imagine that everything is flipped, and we have these red curves, and then we produce as many as necessary, and then we see where they converge, and the result will be a function, and then we ask ourselves what that function is, maybe, and then we discover it's 1 over x plus 1. Okay. Even not entirely, as you can see, 1 over x plus 1 continues on right here, while our polynomials do not continue in that direction. There is no convergence outside, to the left of negative 1. Okay. Similarly, we had a similar example for the exponential function. That was a while ago. Here it is. Yes. A similar situation. Okay, so once again, we started with our exponential function right here. Okay, so we started with our exponential function here, and then through the Taylor approximations, we had these we have a sequence of what amounts to power series. So then Taylor polynomials are, in fact, these are partial sums of a power series. Okay, so partial what that series is, it's also the same as a Taylor series. So if you take all of these graphs together, then they form a power series. And then if you go backwards, which is what we're going to pursue, so imagine that we have those graphs to begin with, red graphs. And then we consider them together and look at where they converge, and turns out they converge to some function which we later on, if we're lucky, recognize as the exponential function. Okay, so that's the backward approach. From polynomials, from power series to a function. And you can see how you're discovering how that function gradually forms. The convergence is quite visible. How the changes are virtually disappear, at least in the middle, around 0. There is virtually no change in the shape of the graph. So that is convergence. Okay. So then we have to, this idea is fine, but we have to, if we want to be able to deal with all functions, we have to be able to produce this result for every power series. So once again, this is my power series. This is what it looks like. So this is called a power series with coefficients C1, C0, C1, Cn, centered at A. Okay, so if I truncate my series, in other words, taking its partial sum, I will always be getting a polynomial, right? So look at it. X appears as a power, and that power runs from 1 to infinity. But if I take only finitely many, I have to have 0 here. If I only take finitely many terms of the sequence, it's a polynomial. Okay, so we are making full circle back to Taylor polynomials. Okay, but we assume that we don't know anything about Taylor right now, but rather all we know is there are series, power series, infinitely many of them, on the variety of series, and then we just want to know how they behave as functions, if at all. if at all. So because they might diverge. So once again, the domain of the power series is the set of all x for which the series converges. The term domain is exactly the same as we have used all this time. It totally fits into the definition of the domain. Remember what where domain came from. You had a function, and then you were asked what's the domain. How you plug in x's into the function, into the formula, say, and find out whether the formula makes sense. It makes sense. There is an output of that formula. Okay, so that's the meaning of the domain. We are in exactly the same place, except that formula is kind of complicated. It's a whole series. So you plug in different values of x into the series and check out, does it converge? If it does, there's an output, and that number is the value of the function. If it diverges, the function breaks down, and so that number x is outside of the domain. Okay, so the domain is, if we treat a power series as a function, then the idea of the domain is the same as before. Okay, so that's not this is not entirely a new definition then, and it is meaningful as well. So because that example, now second example from the top is you don't know ahead of time that you're not going to get everything. That's just not going to happen. There are in fact extreme cases of power series behaving badly. Where am I? Such as let's take something bad, say x n. Okay, so this one is centered at 0. Okay, its coefficients are simply n's. I could hold on a second. How about let's put something big here. 2 to the n. Let's make it extreme. So 2 to the n xn. So in other words, coefficients are growing very, very fast. Okay, so then if I apply, say, the ratio test, or the root test, doesn't matter. In fact, I will write RT because I could take ratio test, root test, same result. So this is my AN. Whether I do a ratio, well, let's do it side by side. I have 2n plus 1 xn over 2n xn, absolute value, like this. So I have 2x absolute value, and now that, well, hold on a second. Oh, I know. Okay, sorry about that. Let's put a factorial there. So there will be no doubt that we have divergence here. That's what I'm trying to illustrate, is a sure divergence of our series. So n factorial times xn. Okay, so if I take the ratio, I have my n plus 1 factorial divided by n factorial, which produces the same result as before, and that result is n. Rather, n plus 1, in fact. N plus 1 times x, absolute value of x. Okay, so remember once again, n plus 1 factorial runs from 1 to n plus 1, all the terms, and then divided by all the terms from 1 to n, you're left with n plus 1 term. Okay, so now we evaluated by the ratio test, we're evaluating this limit. What is this limit? As n goes to infinity, where does this thing go? It goes to infinity unless there's one exception. Unless x equals to 0. Okay, so x equals 0 is good. The rest are bad. Okay, so the domain then is consists of one single number, 0. Okay, so it is atypical in the sense that we don't really care for a series like that because I mean, giving you one value, that's no use. So it could be a point, could be an interval, could be infinite interval. Okay, so these are the possibilities that we have discussed, and now we saw them implicitly indirectly in the ratio test, but the general result is still applies. So let me state that theorem. So the domain of a power series centered at A is always an interval centered at A. Okay, so it's either, so the three possibilities are A minus R, A plus R. Well, there are more than three possibilities, because the endpoints might or might not be included. Okay, so which means that so I could have bracket or parenthesis on the left. I could have bracket or parenthesis on the right, like this. So a total of four possibilities: open, open, close, close, open, close, close, open. So four possibilities. And then there's the fifth possibility, and that's when the whole thing is infinite. So it is 1 and 2, 5 possibilities: negative infinity plus infinity. That's the other one. Well, the third possibility is just the A. Okay, so in other words, as far as the look of the domain is concerned, there are six possibilities: open interval, closed interval, half open interval, infinite interval, that includes everything, or just one single point that is the center of everything. Okay, so then so that's fact number one. Number two, the series converges absolutely inside this interval, meaning so that's a carefully picked word. Inside means excluding the endpoints, if any. Okay, so we don't know. At the endpoints, the convergence might be conditional. In case 3, the series diverges outside by the same token. The series diverges outside the interval. So once again, it is excluding the endpoints. So the picture that I made up previously, like this. So if it is an infinite sequence, say A minus R, A plus R, my point A here, and then outside of it, things are not as good. So this is bad. This is, in other words, bad meaning these points on the x-axis lie outside of the domain, my function, and this is good here. Okay. So the green one is naturally the domain, right here, and then so the theorem answers all possible questions about its behavior, with the exception of the endpoints. So what happens at the endpoints, theorem does not say. Okay, but it's possible. All the possibilities are available. Okay, let me just to wrap up this part by giving you, in addition to these two series right here, just a couple more, and they, for example, give me trig functions. So It looks kind of complicated, but I hope it works out okay. Negative 1 k over 2k plus 1 factorial. It looks very much like a series for the exponential function, except we're skipping the terms. We're skipping all odd even terms. So as you can see, the powers are 2k plus 1, which means that power cannot be even. So we're only picking the odd powers, and we alternate the sign, unlike the exponential function. So once again, if you want to compare it to the exponential function, that's what you're going to see. And what it adds up to turns out to be the sign. So very different behavior from the exponential function, being that's what creates. That's why function does not run away to infinity, but rather keeps oscillating up and down. That's the alternating sign. Now you can probably guess how we get cosine, and the answer is we go once again with factorials, but this time we pick even terms. Why do we pick even terms for cosine and odd terms for sine? If you can guess. Why do we pick even terms for cosine and odd terms for sine? The words are themselves is the answer. Sine is odd and cosine is even. Okay, so polynomials of even degree are even, of odd degree is odd, and so we are making up an odd function from odd degree polynomials, and then respectively an even function cosine from even degree polynomials. Okay, all right, so we'll do some more of this tomorrow.